Hello everyone. Today we're going to explain two Python programs implemented with OpenCV and NumPy, based on the chapter Colorspaces, transformations, and thresholding. And the goal of this code is to demonstrate first how changing the color space helps in segmentation, and second, how geometric transformations modify the image structure.
Let's start with the first program. First, I import CV2 and NumPy, and then I read the input image using CV2.imread in OpenCV. The image is loaded by default in BGR format, not RGB. After loading the image, I convert it into two different color spaces using CV2.cvt color. First, BGR to HSB and BGR to lab. The HSB space is very useful for segmentation because it separates color information from brightness. Instead of working directly with red, green, and blue values, HSB uses hue, which represents the color type, saturation, which measures how strong the color is, and value, which represents brightness. Next, I create a segmentation mask to detect the red color. A key detail is that reading HSB usually needs two ranges because the hue scale wraps around, meaning red appears near both ends and the hue interval. So I define two sets of lower and upper limits using NumPy arrays, and then I generate two binary masks using CV2 point in range. And after that, I combine both masks into one using CV2 point bitwise. And finally, I apply the mask to the original BGR image using CV2 point bitwise. And this produces the final result where only the detected regions remain visible and everything else becomes black. And in summary, this code demonstrates how converting from BGR to HSB makes color segmentation easier and more controlled, especially when we need to isolate a specific color range.
Now the second program focuses on geometric transformations. Again, I load the same image with cv2.amread and obtain its height and width from img.shape. The first transformation is resizing. I reduce the image dimensions to half using cv2.resize with inter underscore area, which is a good interpolation method when reducing image size. The next transformation is rotation. To rotate the image, I compute a rotation matrix using cv2.getRotationMatrix 2D, where I set the center of rotation as the image center, the rotation angle to 30 degrees, and the scale at 1.0. Then I apply the rotation using cv2.warp-affine. This produces a rotated version of the image, and we can also observe black areas because rotating changes the image boundaries. After that, I apply an affine transformation. An affine transformation is defined by mapping 3 points from the original image to 3 new points. I create a transformation matrix, again with cv2.getAffine transformation, and apply it using cv2.warp affine. This creates a skewing effect while keeping lines straight. Finally, I apply a perspective transformation, which is stronger than affine. Here I map 4 points from the original image to 4 new points using cv2.getPerspectiveTransform. Then I use cv2.warpPerspective to generate the final warped image. This transformation simulates a change in camera viewpoint, like seeing the image from another angle.